All good.
All right, welcome everyone. Welcome to the second session on binary search. So if you haven't gone through the first session, I would highly recommend go and watch it because I would be using, I talked about templates, different kind of templates in that session, and I would prefer to use the one which I prefer, but there is no reason that you can't use the one which you prefer. So go ahead and take a look, and then you can have your solution using your favorite template. Shouldn't be a problem. So the idea is, like, normally in these sessions, anybody can come and they go and through different topics, whatever they want to share, and you can go and register yourself as a person who will like to do the sessions. And most likely from next week onwards, we don't have any volunteer. So there are free slots available. So feel free, go ahead and, whatever you feel comfortable with or you want to learn, go ahead and become a volunteer and try to share whatever you want to share. So for this session, I have certain agendas. I would like to talk about it briefly. In previous session, we went ahead with 5 templates, and all those were from my perspective, I covered it in 3 cases when low and high pointers try to merge towards each other. And based on that, there were 3 templates. Fourth template was basically an enhancement, or let's say modified version of third template. So I can't say it's a fourth template, or maybe it's just a third template, doesn't matter. And fifth template was where we had just one pointer, like low, and it was trying to make a jump towards right. So if you didn't go through it, you can go, there is a video for that. And also, people reach to me, do you have these, there were a lot of problems. If you go to our Discord, these were the problems which were suggested to me. There are so many problems, right? I can't cover all of them, unfortunately. So, however, I think Leon reached to me if I have the solution for them, and actually I have the solution for them, all the problems. So if you go down, see, this is now 40-page doc already. It has the video link also and everything, so as a, if you want to look at it, how I solved it using the template, you can go ahead and take a look whenever you want. Okay. So I think there are, I don't know how many people, there are 34 people who already have access to that. So I'm pretty sure, most of you may have access to that, or you can write your own. It's not a big problem. Should be okay. So for today's session, I will start with another basic thing which was not covered in the previous session. That was binary search on double. And how we will do that? First, we will go through a problem, the square root, which is on lead code already. So let's try to solve this problem. So you are given a non-negative integer x, compute and return the square root of x. By the way, guys, yeah, this is a binary search session. So there is one disadvantage, disadvantage is when you already know the session name is binary search, you already are you know a lot. But the main idea is these problems will be more interesting and challenging when you have no idea whether it is a binary search or not. So that part is since we are doing this session on binary search, it's like a spoiler kind of thing. So keep that in mind. So, okay, how would you do that? If you are given x is equal to 4, then the square root should be 2. And if you are given x is equal to 8, then square root should be still 2, right? But if it was 9, then square root should be 3. So, I mean, anybody has any idea, how would you use a binary search to solve this problem? Feel free to chime in.
Yeah, I have an idea. We can traverse. Let's say we have integer. Yeah, integer.
Right.
and we have integer from 0 to integer max. Yeah.
Mm-hmm.
And so we can use binary search from 0 to integer max in order to find out appropriate value. Yeah.
Right, right. Yeah, and you once you find some mid, for example, then
Yeah.
you evaluate using what, like mid into mid equal to less than equal to x, something like that, right?
Yeah. Yeah.
Okay, right. Yeah, I mean the idea is simple. We have solved this problem so many times. So this is my template which we were talking about. I use that. I use the same thing. I realize that this number definitely can't be bigger than, like, the number itself. So based on that, I find a mid, and then I check what is the meaning of okay is important. But then if it is okay, then low becomes mid, else high equal to mids. And in my case, I will show you how I try to uh, go about it. So I'm trying to build something true, 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 false, false, false. Okay. So all the problems, most of the problems, I would say, when I'm trying to use this, I already know like what I want to uh, find. So let me try to write it here a little bit. So sorry. Any reason why this gets unselected? Yeah, interesting.
You can change the pointer under the insert. No, if you click on draw, and there is a or something is there, right? Select that. You need to write something, right? Yeah, that one. Next to the green plus.
This one. This
Next to
one.
that. Next to that, on left side to that.
Okay, this
No, the
one,
other
right?
side. Yeah, yeah. There you can select the type of object, what you want to do. And now
Yeah,
select it.
yeah, I don't know. Like that doesn't seem to work, unfortunately.
Okay.
But it's definitely draw, right?
Yeah, it's definitely draw.
Yeah.
You have to pick a pen and then it should change.
Yeah, I don't know what's going on. Again, another technical difficulty, or I am not good with all these things. Okay, let's try to create a new page. Will that work? And try to draw something here. Yeah, it's fine. Okay, so what I would try to do mostly, I will try to create this kind of thing, like true, 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 false, 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 or you can think like 0, 0, 0, 1, 1, 1. And then I have to become a little bit creative with the questions I ask. And what is going to happen most of the time, you are interested in this value, the last true, if I write it like this, or the first false. If I build a question which is like this, false, 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 lot of false, followed by true, 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 I can build the question like that also. And then the thing which will be interesting is this last false or first true. Okay. So I'm trying to build a question, and since like I'm interested to find the last value in the way I have solved, I will ask questions such that all these guys, even if they are not a valid candidate, like, first one, I don't know, you can see my cursor or not when I hover over. Can you see these cursors?
Yes, yes.
Okay, that's
Yes.
so. Even though I know most likely it is not a valid candidate, it's not the ideal candidate, it's still valid per my criteria. And then I would try to move my low pointer in this case, since I'm interested in this guy. If you remember about the template, I determine whom I want to make a valid guy. So in this case, low is supposed to have all the true values and high is supposed to have all the false values. Okay. If I ask a question in this particular format, then low will be always having a false candidate and high will be having a possibly right candidate. So now once I will show you the code, then it will make more sense. How would I build that? So the question I'm asking, hey, is mid, whatever mid I chose, is less than equal to X? I don't ask whether it is equal to X. So if the value was 8, like X is equal to 8, and like mid value, somehow I jumped at 1. So this is valid. So 1 is a valid candidate, right? 2 is a valid candidate, but since 3, for 3 mid square would be greater than 8, that would start to become false. So all the bigger values will be false, and all I care about is this guy, right? So what do we do in that case? In that case, we know that my answer lies at low, and that's what I'm trying to get at. So, I mean, that's the basic way we will solve other problems also. So any question on this, or I will go to the next point. I will cover the basic part.
So any
And
reason for doing mid less than equal to X by mid rather than mid square less than equal to X?
probably, yeah, that would help me with overflow most likely.
Okay.
Yeah, otherwise if you, like, I know a lot of people always use long, then you don't have to worry about that.
Got it.
Yeah. And if you are confused about this, then hold on. Once you will see more examples, that will become more evident and natural. So don't worry about it. Okay, so the question is, in this problem, we had been given that, okay, the square root is 2, but suppose if you were supposed to ask, okay, find the square root of 8 till, like, 2.8242 up to certain decimal place, something like that. Then how would you use binary search? So we didn't cover that. We in our template, we always had +1 -1, like, we were moving like that, right? Even in this problem, my high is always low +1. But can I do the same thing if I am, like, I have to do search over a real number, not just integer values? Probably not, right? So that is where I will start and go through the basic one more time. And so there are two kind of solutions you would likely see there. One is this one, like, entire logic is same, right? Only thing is now I start to care about certain accuracy level. So here we care about, like, up to 6 decimal place, and my template kind of remains similar. While high minus low is greater than this value, I find a mid, and then I try to run through the exact same search function. Okay. And then I will return still low value. And that should work. If you try to run it, it will work. And then other one is, rather than that, I could also do, like, though I have written epsilon here, but I haven't used it, so I can just get rid of that. Go and run through a fixed number of times. I think I can even say 70 or something. And if you run through, this search these many times, eventually you will have a value. Okay. So does anyone has any idea when to use what, or should I prefer one over the other?
So Roger, I missed this. What is the objective of using epsilon?
Objective of using epsilon in first case, here it is not used, so don't worry about it in this one. But in this case, we were going through high minus low greater than epsilon, because suppose now the question is not what is asked here. Suppose the question is find the square root of 8, and you have to provide the decimal value for that, 2.82842, for example.
Okay.
So definitely high minus low greater than 1 will not work, right? In that particular case. So we are going to squeeze our, the delta between high and low to small value.
Okay.
Yeah. And now it's not anymore like int values, low, high, these all are now double. So that's the purpose. So now the thing is, do you think which one we should use, or do you prefer one over the other? Like, anyone has any, have you given a thought about it?
How do you get the 80 upper bound for the second search?
Sure, we will talk about very briefly on that next. But yeah, for now, can you suggest which one we should use?
I would go with the second one.
See,
constant.
You know everything, Leon. Then what do you ask? Tell me, why would you ask the second? Why would you go with this one?
Because it's constant. It's 80. When the other one, I don't really know how many loops it's going through.
Okay. So yeah, the thing is, both are good, but you should always prefer to use something like this for loop. And the reason being, the main reason is that in decimal, and when you are dealing with precision, floating point precision is very risky. So it's possible you will be trapped in an infinite loop. That's the biggest problem here. And I will show you how I will get trapped here. And then to your answer, Leon's answer, why I chose 80, I have randomly chosen 80. But suppose if I asked you a question like, hey, I'm thinking a number between 1 to 100. And what is the minimum number of guesses you can ask me for any guess, and what is the minimum number of guess you can make and figure out what the number I thought. So what do you do in that case? You try to binary search, right? And then what do? You will say, hey, within 7 guesses, because 2 to the power 7 is 128, you will figure that out, right? Does that make sense? Okay, so if that makes sense, then suppose you have a 2 to the power 64 bit values somehow. So this one can be covered within that, right? So currently now the question just changed, hey, I'm thinking a number which could be double, and you have to guess it. And then maybe I will say, hey, I think most likely in 64, 70, something like that. I'm going to figure out that approx real number. So 80 is just a conservative number on that. And that doesn't change your complexity a lot. So that's why I chose that. And let me try to demo how it will fail. So see, This is the exact same question. I'm trying to search something like this. It's a big number, right? It's a big number, and I chose epsilon as 1e9. It would have worked in most of the cases. But in this case, suppose I try to run this with this while loop, see what is going to happen. It's the exact same code, so no problem. See, it's in a like infinite loop. So what happens even after some time, like due to precision, the way it is handled by our like I don't know what specification it is, IEEE 754, I don't know, something like that. The thing is that it can't determine the absolute difference after certain precision, even when they are very, very close, because there are only certain number of bits which it can handle. So that is when, if I do just this much, now I have fixed like, number of loops here. I have fixed 70. And then it should be okay. Nothing has changed other than that. So see, it finished finally. Also, if you have to go and figure out the exact number of loops, it's possible depending on how many numbers you care after the decimal. But I would say practically, like you don't have to worry about that. Okay, so let's go ahead with that, and that should be okay.
So what is the upper bound, that one, that high, right?
Yeah.
What actually the value, the double value in this case? The
Here.
variable.
Here, this one you're talking about?
Yeah.
It's 10 to the power 9.
Okay.
Yeah. It was just a simple demo to show you which one you should prefer. So even though like you will see code like this a lot, because we are used to doing high minus low, it's preferable to have a for loop with a definite number of jumps. And I know that it will not lead to infinite loop, so I would prefer that one. Make sense, guys?
So Roger, I understand like the above condition in the second version, you say that that might run into a infinite loop, right?
Yeah.
But I didn't understand like why did you choose 70 or 80 to be precise?
Sure. So briefly, I would say I know that most likely around 64, because it's a 64-bit. Like your double is 64-bit, right?
Right.
So that is why, suppose I was thinking, I'm thinking about number 100, right?
Okay.
Then I would have guessed in 7 guesses, I would be done, right?
Correct.
If it was a integer, for sure. But in this case, it is double. I know the overall bits which a double has is 64. So most likely it is something around 64. Most likely it is something around 64 with arbitrary precision. But since I am not that familiar how it is handled, I believe most likely what may be going to happen inside it is some of the part of 64-bit, and I think you have to look at the specification, must be looking at this part, which is, something before decimal part will be this one. And some part would be after decimal. Right. But I know that all of this is less than 64, right? So I know that if I use something close to 64, should be okay, right?
Okay. So basically you are using the number of bits to determine the maximum number of iterations you will be covering.
Right, because every time I can make it in half, right? Doesn't matter what number it was. Yeah. So I'm just, chunking it half, and I'm getting closer to it. So,
Okay. So, okay, got it.
yeah, but if you need a tighter bound, then of course, you can apply some math around it. Like if I only care about 3 decimal versus 9 decimal, definitely I would need less number of loop. So that could be figured out with a little bit math. However, I think this is normally useful enough, but yeah, go ahead and read about it. I can guess how it will work, but since I'm not very, very certain, I haven't done it, I will not, talk about it. But the idea would be,
Mathematically also, I think it makes sense, right? The maximum number in double would be 2 to the power 64, right?
right.
So if we do log of this number, we get 64. So maximum 64 iterations.
Yeah, exactly. That is what we were talking about, right? With that
Right.
100 example, log of 100 is basically 7, right?
Right.
So that's the whole point.
Yeah. Right.
All right. So I think we covered one of the basic thing which I wanted to cover. Then what is the next I want to cover? Hey, yeah, this question someone asked last time, and at that time I was not able to comprehend also because I was trying to explain something else. Now it occurred to me why that will happen. Why ternary search with 2 pointer is not preferred above the binary search? Could be, and I may be wrong, but it just came to me, so I thought I will throw that out anyway. So the question was, so hey, like we have this area with binary search, I go here and I divide my search space in half, right? If we just go something like this, we point to 2 midpoints, we compare, then we can get rid of 2 parts, right? Maybe I totally get rid of this part and totally get rid of this part. So my remaining search space is now just 33%, right? Here my remaining search space was 50%. So why binary search is preferred over this one? So one thing which I could see is that here we are doing 2 comparison, right? There I was just using 1 comparison. If I do two comparison in this particular scenario, right? So what will happen after 2 comparison? My search space will remain just 25%, right? Because if I do another comparison here, I will cut it here, suppose. Here after 2 comparison, we are left with 33%. Here we are left with 25%. So that is one way to look at it. Another way to look at it could be, okay, suppose if that is not the case, and so why stop here? Let's add one more pointer, right? If I add one more pointer, one more mid basically. So now, and if I compare that, so what would be my search result? Because based on these 3 pointers, I will be only left with 1 position, right? So my search space will be 25% roughly against what I started with, right? If I have 3 pointers. So if you try to apply the same logic, the more pointers I have as a mid, search space will reduce. But see, the more, so see how many, after n such pointers, we will be almost be done, right? But that was the linear search if you think about it, right? Now all those midpoints are being evaluated. You get the point I'm trying to make? Our idea was to go through as less check as possible. But with this approach, what I'm going to do, we are making more checks actually. So though it looks like that, hey, this check is, since in our example, it was just finding an index, but suppose this check is basically a binary search, another binary search, or suppose another DFS or BFS, then you cannot take it like, the way we looked at it. So that's the reason binary search would give you a better algorithm. Does that make sense, or do you guys have any question on that? Was the question clear, or if there is any problem with this understanding, I can go through it, or we'll go to the next section.
Maybe,
This was
maybe you
asked.
can,
Yeah.
if you can repeat it quickly once, I think the question was
Okay.
not clear. Thanks.
Okay. So the question was, in previous session, we briefly went over it. That, hey, like in binary search, whenever we make a check, after that check, our search space reduces to half, right? That is clear. So instead of one pointer, if I use two pointer, call it mid1 and call it mid2, then my search space will reduce to 33%. And that is right. That is right. Then the thing is, so does that mean that ternary search, if I call this ternary search, because it has like three parts, is it faster than binary search?
It cannot be.
Right. And that is what we were trying to get at. Right.
Just I don't know, I might be wrong, but I'm just thinking in terms that if you have a very big, let's say array or like a large sequence of numbers, right? So initially, initially it looks like binary search would be helpful, but since we are dividing the array into three parts, our search space into three parts. So if we have a very long sequence, then I guess towards the end of it, this tertiary search would be better. I'm just thinking if we can explore that right now. I don't know.
So in what I found, like, and during last session also, we talked about it, that people have done that test, and of this seems to be faster. And the logical reasoning behind why I consider binary search is better is what I'm looking at after two tests. Like, here I actually still tested it, right? I did two tests here. First test was against mid1, second was against mid2. If I do the same two tests, I am left with just 25% of the search space. Here I'm left with 33% of the search space. The thing is, the testing of it, we consider it to be very like cheap, which may not be the case, right? Because if that is possible, that if you are saying that having two pointers is better, then having three pointers should be even better, right? And then I would say, why not having n pointer would be even better? So in that case, where I am leading to, I am actually going through the entire array. I'm checking all the values to determine it in just one go. But isn't that linear search already if I continue going like that, right?
Right.
Okay.
But Roger, I think there are two things here. First, what you mentioned, in the binary search case, you are reducing your search space by 25%, and in ternary search, you are doing it by 33%. But in case of ternary search, this reduction is happening over just one iteration. And in binary search, we are taking two iterations to reach to a 25% state. So will not that be taken into account?
But what does iteration means, right? It's not like what you are doing in each iteration, you can look at it. So each iteration, you are just going and checking one element, right? You also have to see what does iteration mean in each case, because in this case, the ideal scenario I'm saying, where I will have just one check, in one iteration, I will figure out the number, exact number. but I will do n checks. So in that one iteration, I am going through all the n elements and I'm figuring out the solution, which is exactly the linear search,
Mm-hmm.
right?
Right. Yeah, I understand.
Yeah. So that was actually that was a question from the previous session. So
Yeah.
it was not related to this session, but just want to go over it. So what is left is we are done with infinite loop simulation and ternary search, just intro. Okay, we'll see. So we will go through this problem for peak index in mountain array. And I should have that problem open somewhere. So I think it's another easy problem. So let's call an array a mountain if the following properties hold. So, okay, I guess if you guys did read about it, it's fine. Otherwise, I think most likely it is like a mountain array. So if you look 0 to 1, its value is increasing, and then from 1 to 0, it's decreasing. Here, in this case, 0 to 2, it is increasing, and then 2 to 1, decreasing. Okay. And what we have to figure out is minimum, I guess. Peak index. Okay. So in this case, 1 was the peak index. In this case, 2 was the peak value. So peak index would still remain 1. In this case, again, 10 is the biggest value. And in this case, 5. And in this case, maybe 100. So, okay. So we'll solve this problem and we'll try to see like if we can use binary search here or not. Okay. So think about how would you do that? So a picture will help definitely, right? So in this problem,
I think that element we are looking for is like an inflection. All
yeah.
the elements to the left of it are in what do you say, ascending order, and the rest are in the descending order.
Something like this. Yeah, this is your kind of mountain array. It may not be a linear line, but idea is same, and you have to find this one. Yeah. So here you are, here you are. So how would you find this one? That's the problem. So how would you do that? Like,
So I think this element is special in terms of its neighbors, right? So it has both of its neighbors less than itself.
perfect.
So if we check each element, like we have the mid in hand, right? So we check if A of mid is greater than its neighbors, then that is our element.
Right. Yeah, good idea. So,
But for binary search, you might need to sort it, right? This is not sorted.
it's not
Sorted,
fully
right?
sorted, you can see,
Yeah.
but if you can realize this pattern and the way like Harshit was saying, we can leverage certain facts about how the things are arranged, that may help. Because see, if you are here in the first half, let's say there are two halves, first half and second half. In first half you are there, then what is happening? All these elements, if they are compared against their values towards left, they are greater than their left element, right?
Okay.
What about these guys? If I compare this one with its left, it is decreasing, this guy is decreasing, this guy is decreasing, right? Right? So,
Okay.
yeah. So if I can ask a question like that, hey, are you bigger than your left element? Then these guys will say, yes, I am, yes, I am, yes, I am, yes, I am. And then they will start saying, no, I'm not, no, I'm not, no, I'm not, right? So you have this true, 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 false, 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 and you are interested in the last true. If we can, so the thing was, you have to observe the pattern and you have to figure out like, how to ask a good question around that. Then that may help us. So that was the whole idea. And that is what I may be doing here. is current number larger than the number towards left of it? Okay. Yeah. So I'm also doing exactly same thing in my okay value. And then I'm interested in this value. If you can see, this is what I was interested in, even though all these guys also were satisfying the criteria, but this was of most interest to me. Again, same thing, low equal to 0, high equal to a dot length. Please see low. I knew that I am interested in the low value, right? If I'm interested because that these guys are true. So I provided a valid candidate to the low, and I was not interested on high. So I provided an invalid candidate to high to begin with. If I give a dot length -1, then, and suppose that was the value I was interested in, then low will never reach there. So I would have to do some extra checks, right? So that's why I'm not trying to go into that. And then I find mid, I evaluated against this okay function, and then low move to mid, high in else case I move to mid, and then I exactly know what I want to return. So that was the binary search algorithm, right?
Can
Now,
the last index be the peak, Rajesh?
no, in this problem, you will not have that.
Okay, first and last end. Okay.
Yeah, something like, do you want to any I such that? Yeah, but I don't know whether that was in the problem or not. To be wanted.
So just assuming that there might not be a mountain in this array, then
Yeah.
in that case, your code would return, the element at a of length, right? Your low would be a of length, right?
My low would be still on the last value, because see, low will never reach high for the way I write.
Okay. Yeah, it'll break.
Yeah.
Actually, in this case, it is guaranteed. If we see the description,
Mhm,
right, it's bold that it is guaranteed to be in the mountain. Yeah.
Right. So there are kind of similar problems in our Discord,
So,
I think.
Roger,
Yeah.
I do have a quick question. So, in all these templates, my confusion is most of the time around that. You know that in some problem we do use high length -1 and sometimes length.
Yeah. Okay. So Praveen, were you in the previous session or not?
Oh yeah, I was.
Okay. So I think that was about the second template. So if you watch that session, I don't know, I guess we covered a lot when you do that. So that was the second template in which you will have low is less than high here, or low is less than equal to high, right? Yeah. And then you will see when I can do high equal to mid versus low equal to mid +1, depending on the two.
Not about that. So the initial value you took that high, the starting value for the high is length a dot array length or the such space.
Okay. I see. So you're saying, okay, in this template also this value, you are not sure how to take it, right?
No, so in some problem we start with the actual number of element counting that array will start 0. So my search space is actually on the exact element in that array, right?
Right.
And now here in this one, we are taking that the search space is one extra element.
Right. So that is, yeah, is not mixing the template, but I get what you're saying. In that template, sometimes you see 0 could be there, or sometimes -1. Is that right?
No, sometimes it use high is equal to a dot length, and sometimes it use high is equal to a dot length -1.
Okay, so suppose if it uses high is equal to a dot length, then you can look at what it eventually wants to return. Most likely in that case, it is trying to put the candidate value at low, most likely, because that is why it is putting an invalid value for high. Okay, because suppose you are done with the entire search, And depending on the implementation, I think your low also reached to high, and both are now pointed to an invalid candidate, then you never found the exact element you were interested in. Otherwise, low would give you the element you were interested in. Yeah, I may take a look into the way I implemented that particular second template. But if you can reach to me, with certain question after the session, maybe I can answer well, because it requires certain context.
Sure, I will do that.
Okay.
Yeah, thanks.
But yeah, most likely I would guess this is what is going to happen. That's why you just in the beginning itself, you provide an invalid candidate to that guy.
Okay.
One of the points.
So in the while loop, the if statement, I think in the template that Roger document, they say it will be the if statement will be possibly right. Okay,
Yeah.
it could be wrong, but it possibly right, and else will be always wrong. Okay, so in this case, that's why high will be equal a dot length, because it always wrong. It's gonna go to the else.
Yeah. But Praveen's question is about a different template, Leon. He probably prefers that second template. Second template had two checks depending on if I'm interested in left element versus right element. It was a bit there was certain difference in that, and I believe that that is where we spend most of the time. So I will just say look at these values in those two cases, or maybe after the session, if you give me certain example, I can also look into it. But yeah, definitely it should work, and most likely it should be the reason, but I will let you know.
Yeah, in the third template, Roger, actually you have taken low equal to -1 and high equal to a dot length -1, right?
Right.
So at that time, the bound becomes your -1 to a dot length -1. So if you increase the low to 0, that means you have to go to the full length, right?
You can think that way, but see, I told you that I will build a answer like this. See, if I am building a answer like this, true, 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 false, 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 then my low will always start with 0, because now low is pointing to a valid candidate. If I am basing my question where the answer could be false, 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 true, 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 then my low will always start with true. Oh, sorry, -1. Because it's possible all the values were true, right? And there was no false. So you need a placeholder for your low. So that is why 0 and -1, if you understand when I do what, that will make sense. Here, I make sure that low is the valid candidate, possibly validated candidate. So low will always point to a valid index. In this case, low is going to have, since it starts with false, low is going to start with -1, because maybe all the candidates were valid. So that's the reason. Got it?
Yeah, makes sense.
Cool. So now I will introduce ternary search a little bit, very less. Same question solved with ternary search, and you can look at the code later, but I solved just one problem, so don't take my words for it. But sometimes you will see it, so I thought, why not just introduce where it is used? So it is basically, if you go to CP algorithm or anything, this is the exact scenario where they use it. What they do, okay, if you have mountain kind of thing, you take any 2 pointers. Suppose I take 1 pointer here, and let me take 1 pointer here, right? If the value of the function here and here, I compare, right? If this value is bigger than this value, I can deduce certain thing about my target, right? If I know that target is less than even this value, first value. Then which range I can totally get rid of? I can totally get rid of this, right? This would be useless because I know all these values are bigger than it, right? If the pointer lies somewhere here, maybe here, second pointer, and the target is even bigger than this guy, like even bigger than this value, second value, and I know that F1 is already less than F2, then I can totally get rid of this whole area, right? So this logic of having multiple pointers and then comparing those two guys and getting rid of, you know, 1/3 of the search space is normally used in when you are working with ternary search solution. So once you will see the code, it will make more sense. Exact same problem. Now you know we have three spaces, low, high, and there are three things which could be of interest because we had two mid here, right? So first mid is leaning towards the left. So we used to do high minus low by 2. Here we are saying, hey, high minus low by 3. That is where I will place my first mid. Second mid I will place closer to high. So high minus whatever is the distance between those guys divided by 3. So they are like, you know, equally kind of distributed there. Now, if the value at mid 1 is less than value at mid 2, then anything below the mid 1 is of no use to me because I am searching for the highest guy, right? So I can directly shift my low to mid 1. So what I got rid of in this case is this area from here to here. So let me use a different color maybe. So this area is now totally gone in this case. It's of no use. This was my mid 1, for example. So now my search space has 1/3 value left. Okay. Similarly, if it is the other way that mid 1 is greater than mid 2, then we can get rid of high equal to mid 2. So what does that mean? It's like symmetric to in the other case. Suppose in this case, our mid 1 is here, for example, and mid 2 is here. So I know that this area is useless at this point of time, right? Because all I'm interested is in finding this peak. Okay, and then there was the third case where both of these don't hold true. So that is the case when you know both the side are not useful, and then we move both the pointers towards each other. So basically that could be when suppose both are equal. For example, suppose both are equal. What do you do in that case? If these both are equal, then I know that this is useless. This is useless. So the only area of interest is this much, right? This is my remaining search space. And what I am building is now we have a difference of 3. We used to have a difference of 2 in binary search, but here, after you are finished with this logic, you are left with 3 elements. And when you are left with 3 elements, you can go manually and check, you know, which one is actually the biggest one. So it is just like, you know, going through these 3 values and finding the best index. So I wouldn't recommend, like, you know, maybe go and find more problems where you can solve using ternary search. I haven't spent enough time, so I wouldn't recommend you doing, like, you know, using this versus binary search. But this was a good way to introduce ternary search. So go ahead and try to do more problems if you are interested. But that is my experience with it. During this session, I just did one problem, and I thought I will just show you how it works.
Hey Roger, do you
Yeah.
mind to actually open the third template, what you actually shared last week? So I do see that in that template, you are using length -1.
Sure. Third template. So we had, is it for the first problem or second problem? Do you know which one?
I think for the first problem.
Okay. For the first problem, the third template is this one, right? This one, right?
Yeah.
Yeah.
So you are using here the length -1, that the very first line in this function, right?
Right. So I am using length -1. That's right. And see, in this case, what I will do, low is 0 and high is also possibly right? So what I'm doing, I manually still go and check. See, after I'm finished with this loop, I'm not returning low directly. So that was the, the manual part of it, which was required. So when I started to work on the modified version of the third template, which I use most of the time if possible, then I initialize with low -1 here. You can see in search 4, and high was nums length -1. Because in this case, I made sure that high would be the one which will hold the target most likely. So I said, okay, then give an invalid value to low. See?
Right.
Make
So
sense?
you're saying that, I mean, if we go with the third one and to avoid this, the post processing.
Yeah.
So we should go with the length. And if we want to include the post processing, then go with the length -1. Is that what you want to say here?
So the main point is you already select in search who is going to have your valid values, right? And valid value for an array could be 0 to nums length -1, right?
Right.
So if I want high to be a valid value, I can start with nums dot length -1, right? And see, so what if my first valid value was the 0th element? So you have to give a space to high to reach there, right? Eventually after running through all the loops. So you have to place your low at -1. Otherwise, high will never be able to reach. Because in this template, high never touches low. It is always one step after low towards right side. However, if I choose low to be my candidate, then I start with a valid value for low is equal to 0, and my valid values could go till the last element, right? So low can go up to nums dot length -1. So high has to give space for that. So that's why high will be at nums dot length in the beginning itself.
Okay.
Does that make sense? Or do you want me to draw and I can explain?
Makes sense.
Awesome. Great.
Thank you.
So yeah. So that was the idea of ternary search, and you can go and find more about it on CP algorithm. Actually, this is exactly, if you go to CP algorithm, this is what they were defining. So I didn't write even OK, though I used to write OK. I just did write F, whatever was that. Okay. So now where we were.
So Roger, question on this ternary search. Yeah. Is that an important, I mean, from interview perspective? Is that something that we should know, or it's more from?
I would say probably not. Yeah, probably most likely not. But others, if somebody has seen this kind of problem, they can talk about it. What I can tell you, if I am only able to solve this particular problem and I have very limited experience with it, suppose if I am given an array, given this mountain, I can always I know the way how I can find the peak element now, right? I can cut this in two half, right? So this would be my first half. Once I, using my binary search, I did cut. So this is my increasing part, this is my decreasing part. So now I have two different questions to solve, right? So I can write two binary search, one on an increasing function and one on a decreasing function, and I can still figure out the solution, right? Does that make sense?
Yeah,
just,
yeah, thank you.
Yeah, just using binary search, you can do that.
Yeah.
All right. So let's go to which one? Content array. Search. Okay. This was an interesting concept. Search in a sorted array of a known size. I'm pretty sure some of you will just tell me how to do that. So you haven't been given a like bound of the array. How would you solve it? What happened to this guy? Can I write it? Yeah, I can write it. So yeah, normally we know how big an array is, right? Suppose you want to find some element in an infinite array, theoretically, how would you find it? And suppose it is increasing in this direction.
If it's an integer, you take the maximum value of, I mean, you don't have repeating numbers, right? So then you can possibly say that the max length of the array will be 2 to the power of 31, possibly.
Okay.
One option.
But yeah, like the way they are giving you, they are providing you an interface and you can make a guess and they will tell you whether that number is less than or equal to the target, maybe.
Yeah, is there an upper bound to the max value in the array?
It's not given to you. Suppose you just, the interface will tell you. So
I believe we can start on the smaller, maybe 1 and 2, and then logarithmically jump and verify, right? Whether so I believe it's the last template, right? Where we don't know the it's actually
yeah.
I believe it's a jump template.
Yeah, it is kind of that. That concept is similar. Yeah. So as
instead of dividing, we are multiplying.
Right. So here, as Sujit suggested, he is making starting with the first index and then making a simple jump of 1 size, then 2 size, and maybe 4 size. And once he finds, okay, now this is good enough value, maybe it was even bigger, then high will stop. So high is our higher bound. I can directly use low, high is there, and we can use any template to solve that. Or you can also directly move your low here because you already determined that, these values are useless, right? So your value can just be here. So that is just one optimization. Here, you will just now do your regular binary search where low and high, and then that was.
But this is not sorted, right? The data is not sorted, right? It is sorted, okay.
Yeah.
But ever increasing.
Yeah, it's always increasing function. It's sorted. Actually, the problem is on lead code, but it's a premium problem. That's why I don't discuss it. But in my doc, you can find the link to the problem and you can go try to solve it yourself. And I think on Discord, I think here in Geeks for Geeks, you can find this problem here. Here is the problem on lead code. All right. So I think, that concept is done. Okay. Search on a 2D matrix, and then what is find minimum in rotated sorted array? Okay, we do want to do that. That should be fast. Search a 2D matrix. I think it's a very simple problem. So you are given this sorted matrix. So you can see the value 1, 3, 5, 7, 10, 11, 16, 20, 23, like that. So if you unpack this, basically it's a sorted array, right? In 1D. and you have to find whether a target is there or not. So the thing is, if you were given just a 1D array, we already know how to do that. So the only complexity on top of it, the previous problem is how to do it in like 2D version of it. So I'm pretty sure most of you know how to do that. I will not spend too much time, but idea would be you have to be aware how these rows, like there are 3 rows, there are 4 columns, each row has 4 values. How can you map that mathematically, basically? So if I am landing to, like, suppose by chance on 16, and if I am searching for 3, I need to know that where my high is going to be versus my low is going to be, right? And that could be done with this simple trick, you know.
Yeah, you just find the row and then you do a binary search on that row, right? Find the row index and then do a binary search on that row.
Yes, you can think like that also. Or just treat it as, like, the question is, suppose if I give you an index, can you uniquely determine where does that, like, you know, where it exists within the 2D array, right? So I would say index 0, 1, 2, 3 is in first row, 4, 5, 6, 7 is in second row, right? So if I says this value is like 7, right? 1, 0, 1 to 4, 5, 6, 7. Okay, so if I give you 7, index 7, if you can uniquely figure that out, hey, it is in row number 1 and column number 2, because 0 based I'm looking at, then we can directly, you know, access this element. So for me, then this problem is converted in a 1D array, right? 1, 3, 5, 7, 10, 11. It is, I will do everything as if this is a 1D problem, as long as given on the index, I can access it in this matrix. And that is what I'm trying to do. I say, okay, my high could be R into C minus 1. R is number of rows and C is number of column. So this is the high. And see, if I give high a valid value, that means eventually I am interested in high. Okay. And that's why I give low a -1 value, that I don't want it to handle a case where it could be invalid. Sorry, it could be valid. It's always invalid. I will try to do that. So I'm trying to do the exact same story, and we'll go through the OKs shortly. But then I go, if things are okay, high will point to the value, otherwise low will point to the value. And once I have value I, high, and high will give me, hey, okay, maybe your index is 2, or I don't know, this index is 1. So I'm not sure whether this is definitely right. So I will check, okay, whatever value I have or whatever index I have, let me map to the matrix. So how I map to the matrix, I just divide by the column, because see, it's a 4 length column, right? So I can divide it to figure out which row it is mapping to. And then using this modulus, I can figure out which column this guy is mapping to. And then I uniquely figure out, okay, this value, let me check whether that value is target or not. And that's what we have been doing here. So here we did.
So basically flattening the matrix into an array and then searching for it.
Yeah, exactly. Conceptually, I did that.
Okay.
And if I have to write this OK function, normally I try to comment. I don't know why it is not there. We will have something like this. And I'm interested in the first row. And the question I'm asking, hey, is the value greater than equal to target? Because then all these values, last values will be true, 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 true. And all I'm interested is in first occurrence of this. And that is why I was telling you in the beginning, if you understand the second question we did, where we are finding lower bound and upper bound. If you know how to do that, all or many problems will get converted to this kind of situation. So what does that mean? Think about, this is 0, 0, 0, and this is 1, 1, 1. I am finding lower bound for 1 in this particular case. If I had sometimes I do this and this, in that case, I am trying to find upper bound for 1, right? In this case, if I'm interested in this false, then basically I'm trying to find upper bound of false or 0, for example. So all this goes to the second problem which we solved. Eventually, like, you can generalize to that. Okay.
So if we would have gone by the second template you just wrote, then the OK function would also change, right? It would have been less than equal to.
Yeah. In that case, yeah, you can do that. And I think I have some problems where I didn't write OK function. You can even write things here in line. But most important thing is, after that, you go and check both the guys who is giving you the valid value.
No, I'm saying had we taken low as 0 and high as R into C, then it would have been your OK function would have been less than equal to, right?
Oh, exactly. So yeah, because what you are going to do is you are converting in this format, right?
This one,
yeah. So yes. And now you know how you can build this question, right? Asking right question. Because I already know how I want to solve it. I will ask that kind of question. And then I know I'm interested in this value in that particular case, right?
Yeah. Yeah. Awesome.
Yeah, cool. So that is this question. How are we doing on time? I want to, hopefully we have enough time because next section is more interesting. Search a 2D matrix, find minimum in rotated sorted array. And let's see, what is that problem even? Oh, why do I want to do that now? So the thing is, yeah, it had certain pattern. So what we can do that, either you guys can look at it or I can solve it, but there are a couple of more problems on rotated sorted array. Maybe if I do next session, I can do all of them together because then that would be faster. Does that make sense? And it's easy also.
Yeah, I think that works.
Yeah, though I can give you like, very quick overview of what I'm trying to, actually we have solved this problem already if you think about it. Rotated sorted array, how it will get converted to is like this. Suppose if the array was increasing, it would have looked like this, right? But now we have rotated. So maybe we shifted these values, right? We shifted these value towards left. Then how will it start looking is one section will be like this and one section will be like this, right? Sorry, I don't know. This is our coordinate. So yeah, if I draw dotted line, yeah. So now, see these two values, I can say 0, 1, 2, 3, 4, 5. So 4 and 5 are suppose here. And 0, 1, 2, 3 is here, 0, 1, 2, 3. You have to find the shortest element, right? Shortest element. So now you basically have two such sorted sequence and you can find where this value, minimum value lie. In the hill kind of situation, we were interested in the highest one. In this one, we are interested in the lowest one. So again, you can ask the similar kind of question to the neighbor, and based on that, you can figure that out, right? So if 5 asks, hey, am I bigger than you? To 4, answer will be yes. If 0 asks to 5, am I bigger than you? Then answer will be no. If 1 asks, am I bigger than you? Then answer will be Yes. So see, this 0 has this unique thing that this is the only guy who will tell that I'm smaller than the element towards my left. So now we have to be careful how I ask the right question to still make that true, 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 false, false, false condition. So the question I am asking is considered number less than equal to the last number. So if this was the case, so I think that example can still work. So suppose the example we were having was like this after the rotation. If it was, probably we had 4, 5, and then we had 0, 1, 2, and 3. So what will happen is considered number, suppose mid was at 5, then is considered number less than equal to last number, answer will be false, right? If 0, we go to 0, is considered number less than equal to the last number, and then answer would be true. Yes, because 0 is less than equal to 5. 1 is less than equal to less than equal to the last number. Oh no, last number is this guy, because this is kind of pivot. Yeah, so last numbers, yeah, I was confused. This one, this is your pivot. And why it is important? Because this is where rotation took place. So if I compare things against this, I will eventually get a right answer. So that is why if I just ask the neighbor, which I was asking in this particular problem, like, when things were like this was the pivot, and then just asking to the previous element, it was working. But in this case, if I ask that, I may get true, 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 false, false, maybe again some true, truths, and that is what I don't want to go into. My eventual goal is that I should have false followed by true, or true follows by false. And that is why thinking about asking the right question is very important. Now, if I compare everything with 3, so 4 will say, yes, I'm definitely less than 3. 5 will say, I'm definitely less than 3, right? So you will have, if I ask that kind of question, are you less than the last number, less than equal to, greater than equal to, then that would be the case. Is 0 greater than equal to 3? No. Is 1 greater than equal to 3? No, no, no. And if I build my question, then this was I was interested in, but I did build the question in a different way, that is 4 smaller than equal to 3? No. Is 5 smaller than equal to 3? No. Is 0 smaller than equal to 3? Yes, 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 yes. So, and I was interested in this particular case 0. So you know that most likely I would be trying to have high here, right? And that is how this would be solved. Yeah, high was the one.
Roger, how about comparing both the side actually, instead of comparing just the last element, right? Because any element, if it is a pivot, then it has to be smaller than, it's actually smaller than both the sides, right?
Yeah, because we rotated in this case, right? So 3 was giving me the right property against which I can get this kind of behavior.
Right, yeah.
Right. And that is why now after you do that, then it becomes trivial. But yeah, getting to that will take you some observation how your data is, how it is arranged. So yeah. And there are more problems on rotated sorted array. I highly recommend that. My doc has that also, so you can take a look how I solve those. Where is the next problem? Where we will, this is the important thing. When can we use binary search? And this is totally my observation. So don't take my words, and you guys can suggest your your way of thinking about it also. Sometimes it is very apparent and sometimes it is not. So if I know an array is sorted, then of course, like, what comes to our mind is this a binary search? Like, is possible to do that? Of course, it is very clear. The second thing is sometimes your problem can ask, find the minimum of something, sometimes maximum of something. Both are like, symmetric. So of course they go hand in hand. And then you can consider, is it building into any, like, monotonic way? Can I think about a function or where I can map it to, and then you can try to figure that out. I know that minimum maximum you also do with, like, DP. So of course DP is another way to think about it if you are searching something. But thinking about binary search is yet another tool which you can have, and try to see if we can map it to that. Then there could be maximum of minimums, minimum of maximum. They are similar, but when this kind of thing happens, it's a strong suggestion that maybe there are a lot of minimums. For example, is one maximum out of that I'm interested in? So binary search could be helpful, and you will see in some problems like that. Then, of course, if monotonicity is clearly evident, then of course, like, you don't have to do anything, but you may have to spend some time to think about it. And how I do that, I will tell you. It may not always work, but I will give you how I think about it. Then bound of the problem and expected complexity. Yeah, that is one, another way. Suppose you can check the bound of your problem if you are working on any online JIS, if you have that, like, in front of you. Then when you see that, hey, maybe O of n is not feasible, but O of log n seems to be feasible, because there are not many things which can do better than O of n, either O of 1 or O of log n, then maybe I should think about it, right? Another one is, you can think like this. If someone gives me an answer, can I check whether it is right or wrong, right? If like, we will do, I think, Coco eat bananas. If somebody says that Coco can eat bananas in 6 days, then there are two things I can think about it. If Coco can eat bananas in 6 days, for example, I definitely know that it can eat bananas in 8 days also, 10 days also, right? Another thing, can I simulate it? If, like, in algebra problem, what you do, you are given x square is equal to 4, for example, and somebody gives you an answer that 2 and minus 2 are valid answers. So can you go and check that value? Even if I don't know how to, like, solve an algebra problem, I can try to put the values and see if this gives me a right answer. Then I can verify that. So if I can just verify the answer, then that gives me a hope that, okay, maybe I can binary search the answer. Okay. Another one I find useful is if someone gives you a problem where the answer is, they will ask, hey, the answer would be accepted if it is, valid till 6 point after decimal place. It's a very strong indication that it could be a binary search problem, because some way you are not looking for accurate answer. You are, breaking your problems in different small parts, and finally you are going to reach a place where it will be within the, accuracy range of the problem, and then you can go and solve it. So that is, guys, the big picture, like, where you should think about it. Unfortunately, our session name is binary search, so now we are already biased towards it. So it may take some more time to, like, get to that intuition. And sometimes still the intuition could be wrong because maybe we didn't figure out whether a function is monotonic or not. It is sometimes very apparent, sometimes it is not that apparent. So that is a challenge. But yeah, this is a good start in my opinion. So yeah, to this idea, yeah, I don't know, I want to do that problem or not. But quick question, like, for example, suppose you are given like lot of points, be 5, 6, 2, 3, 8, 9, and so many such points. I don't know how many. And then they ask you how many triangles you can form using this side length, all these side lengths, unique number of triangle. Okay. So of course there is one brute force approach where you will try all the triplets, right? 3 sides, and then you can count it. But you are getting a time limit exceeded exception, unfortunately, if you try to do that, right? But we know one certain property for sure, where we know that, hey, if there is like, 3 sides of a triangle, if suppose A is the smallest, B is the second one, and C is the largest one, then I know at least A plus B has to be less than C, right? So can we use that extra information in our favor? So see, we are dealing with some ordering, like I already expect A to be less than equal to B, and then C is possibly bigger than these values, right? Possibly, I'm not saying definitely, but possibly. But A plus B has to be, actually, yeah, A plus B has to be less than C, right? Otherwise, if it is equal to C, then this will be a line, right? Yeah, it has to be. So in that case, looking at the bound, you can figure out, and this is the exact problem. So I guess you can go and try to solve this problem. But see here, looking at the bound was 2 into 10 to the power 3. If you write a O of NQ solution, you are going into the range of 10 to the power 9, so it will not pass. So immediately you can drop that idea of implementing that solution for sure. So what is the next better thing? Maybe n square, and then something, maybe logarithm may work, right? Because then we will be in the range of 10 to the power 6 into some constant. So log of, I don't know what is the bound, 10 to the power 3. It's still like, we will be into 10 to the power 7 range, so it may pass. So we'll evaluate that idea. And sorry, I'm like, running a little bit faster, but we have to cover a lot of other things. But you guys can interrupt me if question is not clear or answer is not clear. But what we are doing exactly that. I have a loop for A, right? First I sort the lengths, Then I have a loop for A, loop for B, and then I want what is the target C can have. C should not be bigger than, A plus B. And in the remaining range, I just do the binary search for this value of C, right? And I see where it can lie. So if it can lie up to a certain relation, then I just, find how many elements are within that. So visually it will look like something like this. Suppose you have this value. There are so many points. And suppose your low is here. That low guarantees, hey, C cannot be bigger than this. And if I have A here, I have B here, I know, okay, these all values are valid for C. So I can directly add these values. And then I will shift my B next time for each A. And that is how it is going to calculate. So that was just to demonstrate that sometimes the bound can give you extra information. Sometimes if you are not able to see, like you use this the way it was intended to give you, it's good to think that way. Yeah, but if you thought
Hey,
about it,
Roger.
yeah.
So what is the lead code number? Which problem is this?
Sorry, this was not on lead code. This
Okay.
was on a different ad coder, but I think I should have that problem in my doc as well with answer.
Oh, okay.
So
Okay.
yeah, you can always refer to this.
So this doc is shared on Discord, is it? Where is this? Is this shared or?
Yeah, in the Discord you can, or you can ping me. I think on algo session, weekly algo session, I think I shared a doc, I guess, somewhere. After the previous session, I just did it. Hey, yeah, this is the document.
Oh, okay. Okay, great. Thank you. Yeah.
If you click on it and ask for permission, I will just allow you.
Oh, okay.
Okay. So yeah, what is left now? These are the interesting problems. I think you guys have solved it so many times. How are we running on time? Okay, it may take us some more time, but so this is the binary search the answer part. Okay, so this is one of these ideas. So let's go through a few of them. So why don't you read this problem in 1 or 2 minutes. I will be back and then we'll see how we are going to solve. Just 4 problems we'll solve mostly, or maybe less, we'll see. All right, I'm back. So the problem is, okay, find the smallest divisor given a threshold. So if the numbers are 1 to 5 and threshold is 6, if I divide everything by 1, we will have 1 plus 2 plus 5 plus 9 is 17. If division is by 4, then 7 by 5, then it is 5. Okay. So one thing to look at it is, if I divide by a bigger number, this value will reduce. Each values will reduce, right? So eventually their sum will also reduce. So there will be a monotonicity there for sure, right? Because if we are interested in the values, this will be like this, right? Dividing by 1 gives me 17, dividing by 2 will give me value less, by 3 even lesser, and like that. So it definitely falls in our category. Okay, so that's good. We can then, it is telling you the threshold should be 6. So if you divide by 2 bigger numbers, suppose I divide by here by 10, what will happen? Everything will become 0. If everything will become 0, then this breaches this limit of 6. Even dividing by 5 was giving us value of 5. So even 5 was not, having that value. So now our question is, can you find the maximum number with which you can divide it and it is still within the threshold, right? So I will look at my, like this okay logic. This is the core logic, how I want to answer it. So I'm preferring to go to this kind of scenario. I want to return this value true. There will be a lot of false and a lot of truths, right? So the way I'm planning to say, I'm saying if you divide by 1, then that is false. So too big the value is false for me. But that also means then a higher value, like a smaller value is okay for my case. So eventually we'll have a lot of truths here. And all we are interested is in this true. Okay. Now, suppose someone gives me, hey, can we do that in, does 5 satisfy the criteria or not? Okay. So I have to be able to, if I can validate that, means I can simulate that, then that should be good for me. So I think I can do that, right? Because all the numbers are given and I exactly know what is the threshold, like, am I within the threshold or not? So all I am doing is I go to all the numbers and I'm trying to see whether I am within threshold or not. If I'm within the threshold, that's good. Otherwise, it's not good. Also, sorry guys, here the division is a little bit different. So if you divide 7 by 3, it's not 2, it's 3, right? Dividing 10 by 2 is 5. So the way they are dividing, you have to be careful about it. Okay. So that's why, do you guys know about this trick, by the way? How to do that is basically, suppose you are dividing 7 by 3. So 7 by 3 should not be 2. Integer division will give you 2, but you want it to be 3, right? But 9 by 3 is fine, it's 3. So how do you do that? Is basically just adding 3 minus 2, like 3 minus 1 divided by 3. And why? Because see how division will work. This is 7 by 3 plus 2 by 3, right? So I know this will become 9 by 3. Like actually it will become 9 by 3. But the way division works is if I do it alone, this is 2, this is 0, right? So that is why we are trying to convert using this value 3 minus 1. So it will promote all those guys which are smaller than p minus 1. So suppose the value was, okay, 6, 7, 8, 9, right? When I divide by 3, this is 2, this is 2, this is 2, this is 3. I want these two guys to become 3, but not this one, right? I don't want this to be. So I can add this distance as an offset, and that is what I am doing here, 3 minus 1, and divide by 3 to derive that. It's a very common pattern. You can think in a different way. But what happens if I add plus 2 value? I know that these guys are going to at least reach, 7 will at least reach 9, 8 will at least reach 9, it can even go beyond it, but that's not a problem because even if it goes beyond it, I know it is not going to cross the limit of 12 the way I am choosing this value, because this value is p minus 1, right? This value was p minus 1 if I'm dividing by p. So that you will see quite often, the problem. So I thought I will just tell you. Or if you know other way to do that, it's fine, but logically should be okay. So yeah, so these guys will start to give me, okay, it's not feasible if you choose 1. If you choose 2, it's not feasible, things like that. And then it will start to become feasible. And all I want, okay, what is the best feasible value, or what is the least value which is feasible, or smallest divisor. If you see, the problem was smallest divisor. And so high is in charge of the value, right? Because true is towards right. And that's it. And all the questions, logic got encapsulated in the OK method if I could do it. So
Roger, one quick question. What
Yeah.
would be the time complexity? Because we are iterating over all the numbers in the OK method, right?
right. So this part will always be log of this
Yeah.
value, right? Whatever is that. So we can multiply by that. And the rest part is the complexity of OK. So if you are going through the number, it's like n here. If I call it n, so O of n into log of this value, right?
Oh, okay.
Yeah.
I think the high can be the max of that particular, or max plus one in your case, right? Max plus anything more than.
Yeah. I mean, that is another optimization you can do, that you can always choose the high in a way which makes sense. It's too big value, and what I did, maybe I directly took this value depending on all test cases. But if you try to go over it once, you can figure out the highest value which you can be interested in, or the lowest value maybe. You can figure out the bound based on that. And
Okay, yeah, thanks.
So why did we use implementation like int into for the high?
Which one? Here?
Why did 1e6?
So see,
instead of just done that nums dot length, right?
No, so my high is basically, I think, what is my high? Is it
threshold actually?
What? Sorry?
I think threshold, right? Whatever the maximum.
Yeah. So high is basically, I think I chose this value.
Based on the constraint.
10 to the power 6. Yeah.
Here, you can see that, right?
Okay.
So I'm looking into the constant, and then that saves me time, plus also like it will always be valid for the test cases, but it's a good idea. You can just write one for loop to find the ideal high if you are interested. Okay. Yeah. So another, I have been talking about this a lot, so because it has a lot of likes, so why not? So this problem is where you are given piles. I think this is 3. There are 3 bananas in this pile. There are 6 bananas in this pile, 7 and 11. And there is a coco who eats banana at a different speed, I guess. The eating speed of K. So the question is, can he finish eating the bananas in 8 hours? And also the thing is, like, suppose there were 7 bananas and his speed was 3, then it will take him 3 hours, because he will eat 3 bananas, then 3 bananas, and then he's left with 1 banana. So he has to finish that one before going to the next pile. Okay. So the question is, return the minimum integer case such that C can eat all the bananas within H hours. Okay. So what you can think about it, two things. If somebody tells me that C can eat bananas, can I simulate that? I know that I can simulate that. It's a good thing. I think most likely my research will work. Plus also the observation that if C can eat bananas in 8 days, C can eat bananas in 10 days also, right? Or 12 days also. And when I think about it, I don't think like just next value. That is what I was telling you. Because what happens when you will think, hey, if this is possible in 4 days, will it be possible in 5 days? What happens? Our mind still tries to struggle with the idea, is it feasible or not? Sometimes it's very clear. But if you ask the question, if it is feasible in 5 days versus it's feasible in 500 days, for example. So mind stops there. Our wisdom takes place there actually. It will tell you, come on, Of course it can do, right? So that gives you that, you know, idea that, hey, yes, definitely possible. It's a monotonic. Go ahead. I don't know whether it works for you guys or not. For me, it works. So I think a big value. So this problem is again a simulation problem, and it's most likely what I'm going to do, again, I'm interested in the high value. It's because low is -1. It's the same boilerplate code here. If okay, this is given, piles is given, this is a candidate given, h is the maybe the speed. And what I am going to do, I will ask, hey Coco, can eat banana in h hours or not? If it can eat, then great, then I can, let me try to find a better value of I. So let's go through this common idea. So then it's just a simulation at that point of time. We go to all the piles one by one. We have a speed of mid, and then we see, okay, what time, what is the time it will take to finish him eating all the bananas or her eating all the bananas. And then that's it, what is happening. By the way, guys, this is exactly the same thing written in a different way, where I was telling you, you can add mid -1. So you could have written this equivalently like this, and that should have worked, yes. P minus, so P -1, okay. Why was -1, by the way? Let me think. What was 1? Okay, okay. Here. This is also going to work. Oh yeah, so this is basically, I broke it down. See, these two guys are equivalent, right? If I try to write the same thing, this will become P -1 divided by mid +1, right? So it's the exact same thing. If you write it, this will be P -1, bring this on this side, plus mid by mid, which is equal to 1, right? So basically it's the same thing. That's it. And then we confirm that it's feasible or not, and then we are done. Okay, so nothing exceptional over there. And I have intentionally kept this session to be like, you know, doing not very hard problems, and maybe we'll need another session to do harder problems. So let's see if we can do that. So just try to internalize this pattern, the problems we are handling, the way we are handling, and then that should be good for next session. Another problem is like capacity to ship package within D days. Okay. So in this problem, what is, and I asked you guys to look at the problem. So I'm trying to give you a very brief overview. Hopefully you have seen it. But here you are given like, you know, all the weights, and you want to, you know, transport these packages within 5 days, for example. Okay. So you have to tell what is the least weight capacity of the ship, which can achieve that. Okay. So again, my one idea, if somebody tells me it is possible in 10 days, can I simulate that? So I think I can simulate that. I can go through it. I will try to, you know, pack it, and I will see whether it is feasible or not. And that is one way. Another thing is, if I use a bigger capacity of the ship, so instead of like, you know, suppose ship used to take 50 lb or something, now if it takes 5,000 lb, is it possible to ship within these many days? Obviously, right? Maybe then everything could be shipped in the very first day, right? So definitely there is some monotonicity here. So that is giving me a little bit intuition that, okay, try that. So I will try that. Okay, these are just the example how they are trying to do it. So again, guys, these values, if the value looks something like this, I must be using something from here, yeah, in the constant. But you can look into the array and figure out a better value depending on how you want to do this. I just go to the constraint because it saves me time. Again, my question was, can we ship all the packages within time if each SIP can carry this candidate value of weight? If it is too big, then I know, of course I can. Of course I can. If it is big, there will be a certain point where it will be the last value which can SIP. And then if the SIP can carry very small items, then of course it will not work. And then that's the core logic will be in this simulation part. And that is where I'm going to go through with all the weights. If just one weight is big enough, bigger than the capacity of the ship, then we cannot. Suppose just one item had weight of 50 lb and my ship can only take 40 lb, then I can immediately say that it's not even possible. Otherwise, I will try to pack as many items as possible. And I will say, okay, how many required days are there, which I can do. And then we'll continue going through that, finally figure out what was the actual days, and I will compare it with what was the threshold day which I was given. And then I can determine whether it is possible or not. So you have that pattern going on, right? At this point of time. This is kind of boilerplate thing. You already know where low is going to, which one will give you the answer. You can decide on that. Based on that, you can ask the right question, and you can simulate it. So once you are able to figure that out, then that's it. It's all simulation code at this point of time. Nothing else is, very hard to do that.
So why did you multiply high by 500?
High by 500. High by 500. What was there? Oh, the weight was 500, right? So my SIP capacity, right? If all elements are of this size, 500.
Okay.
Right? It's possible if all of them are like that. Actually, now when you are saying that, I'm thinking maybe I should also do. Oh, no, my high was right. Okay. Otherwise, if high was supposed to carry a wrong value, then I would have done +1. But since high is the guy who will have the right value, I will leave it there.
Right.
Yeah. And then the last one for today, it's even though hard, but it's kind of similar. So you are given sweetness ranges for different chocolates, maybe. Yeah. And then you can cut it in different pieces, but adjacent pieces. So for example, if you look at this array, how we are cutting is 1, 2, 3. Then again, second cut has 4, 5. Then just 6, just 7, just 8, just 9. So you have 5 friends. So eventually you have to cut it in total 6 pieces. And you are trying to get the maximum total sweetness which you can achieve. Okay. But you have to take the minimum out of it. So that falls in that category where you are trying to maximize something on minimum. So yeah, that's most likely could be done with binary search. And that's a good intuition we can have. But also, if I ask a question, hey, if I can get, ideally, X is the answer. Suppose I can get X sweetness. Then if I ask, can I get X minus 5 sweetness at least? Of course you can get, right? So there could be a way in which I can convert it into a true, false scenario if I try to simulate this thing. So at this point of time, I know that much. Most likely it will work. And then this is the value here. So maybe I again use the value from here. So what I'm saying, okay, how many persons
Can you
are,
repeat the problem? Can you
yeah,
repeat the problem?
sure. So the problem is you are given chocolates, which you can cut in multiple segments, right? And you can divide these chocolates to your friends. Okay. And then you have, suppose in this case, you can see you have 6 pieces of the chocolate. One piece has sweetness 3 plus 2 plus 1, 6. Another has 9. Another has 6, 7, 8, 9. All you can only eat the one which has the minimum sweetness out of it. So you can either take this one, 6, or you can take this one, right? Because your friends, you have to be like, make sure that your friends either get at least that much sweetness which you got, or they can get more than that.
So, K is what? Sorry, what is K? K is 5. What does K mean here?
K is your number of friends, you can think.
Oh, so that's why it's a number of partitions will be K plus 1, is it?
Yeah,
Okay.
Because you also have to eat yourself,
Okay.
right? So they are saying, yeah, your K friends and K plus 1 pieces. So I'm saying, okay, how many persons are there? So K plus 1 persons are there. Okay. What is the max we can get is whatever it was the limit divided by persons plus 1. And please see, I'm doing plus 1. When I'm doing plus 1, you can guess that low will be the one which I would be interested in, right? Because
Yeah.
I'm choosing an invalid value to make sure that high doesn't have that. So I go through the same boilerplate thing now at this point of time. I try to do okay. I will simulate this piece later, but I can write this code before I start even writing the okay thing, because my core idea is here already done. Then I will start with a good question to ask, hey, can I get at least this much sweetness, right? If I can get, then it's great. Otherwise, I may not get, then the value I'm interested in, what is the maximum I can get out of those values? So if I suppose in theory in this problem, I can get 6 sweetness, but I don't know. If I ask, can I get at least 1 sweetness? So the answer would be yes, you can get at least 1. You can get at least 2 sweetness, and like that. After, if you ask, can I get at least 7 sweetness? Then answer would be 7, right? So all that depends on how we are asking that question. And then again, what I'm saying, if this is the sweetness I can have, minimum sweetness, can I cut it into, more than the number of persons which I have to provide the sweet to, right? So suppose 1 was the sweetness level I want to have, then of course I can do it. I can give it to definitely 6 people, even more than that I can do. But since we have only 6 people, no problem. I can take 1 and the others can take 2, 3, 4, 5, 6. And maybe I will give this big chunk to someone who is really, likes chocolate a lot. So yeah, that's the simulation. If I can't do it, then I will return false. And that's
actually this problem, right, Roger? I mean, I'm just trying. I have not done this, okay, but I'm just thinking intuitively. I'm still not able to, or maybe I need to think about it a little bit. I'm not able to relate this to a binary search because the reason for that being that first of all, I mean, if you look at the explanation, right, it basically says he's dividing the chocolate into that many these particular variables, or these arrays, right? Right. So my thinking will go in that direction probably.
Sure.
To see how I can divide it. So,
yeah, even if you do that, so think about it. If you divide in a very small sweetness level, right? If you divide in a very small sweetness level, what will happen? Suppose 1 was the value. So you can divide 1, then 2 also satisfies. So these all guys will satisfy that criteria, right? So I can satisfy how many persons with that? as many pieces are there or not, right? If I have only 6 persons, I can definitely satisfy all of them and I can get the minimum out of it, of course, right? But if I say, can I get, 7, for example, 7 sweetness, then what I can do, I have to get 7, then all others have to also get at least 7.
Okay.
What will start to happen now? See, more pieces are given to people. So what will happen? There will not be enough of items left to give it to them. So that is why it is monotonic that way, right? You cannot satisfy everyone if the sweetness, minimum sweetness is, desired sweetness is bigger than certain threshold.
Okay.
So if it is less, I know we can. If it is huge, it's not. And if you try to simulate, it's a monotonically, that behavior is there. So,
okay.
Yeah.
Okay.
Then you can create your own question around it, how you want to do it. But then at least you will be able to think why you should think that way, I guess.
Right. Yeah.
But
Okay,
are we
thanks.
checking anywhere if we want to divide more than the array length?
Divide more than the array length.
Like if I have like only 10 chocolates and I want to divide it by 20 people, that check.
Then actually this criteria will be always false, right? So you will get false right away. You will come to the false, and then what will happen? You cannot satisfy at all. And I don't think whether this problem tells you that is feasible even or not. It is just asking what is that value which you can do it. So most likely, I think the question is built that you can always do it.
You can always divide, okay.
Yeah, otherwise there could be, can you do it? And if you can do it, then what is that value? Otherwise,
You should return -1 or something. Yeah.
Yeah. Then in that case, what I would have done, I would have to check actually, is that even feasible or not? If it is not feasible, then maybe just tell that, okay, it's not feasible.
Yeah, the first check itself, right? In the first loop.
Right.
First condition where you are initializing the persons and int, at that point itself, you can do one check to make sure, then you can just get out of the loop.
Right. Actually, there are a couple of questions in that where I had to run this kind of check. I forgot, but in this document, there are few problems based on that, which will have that kind of check if it is required. But yeah, that's it for today's session. We did cover what? What we covered is
many things.
Yeah, it was a bit rushed, but I think, yeah, we have to do, because I have to cover so many things. I don't get time to do it. So like we'll go through all the theories which was left over, like, on doubles, infinite loop, now about it, a little bit about ternary search, which you can go and look into it. And then this binary search idea is very, very powerful, and you get a lot of problems on that. And you can see just on, where is my Discord? I don't know where is that is. So see, I think all these problems where I think that's why I have a separator around it, is all this directly binary search the answer. So there are some new value problems also which I solved, which is like, which will have like, you will be doing some BFS around your OK function. It's not straightforward. So what will happen when you are trying to run this OK function? Actually, now it's a total graph problem you are solving inside this, and you will have solution to that here somewhere. If I have time, maybe next time I will cover one of those, but I don't know.
For the last problem, Roger, could you give an example when it not monotonically increased, therefore it's not a candidate for binary search?
For this one you are asking?
Yeah.
So
we know this is a binary search because it monotonically increase, right? When we check, I'm asking if you know, we ask the true and false question, but then when we do the OK function, it's not monotonically increase, then it's, you know, if you can give, whether you can give an example to see that, you know, this, it's not a monotonically increase, therefore not a, we cannot do it in binary search.
Oh, so you're asking like the questions where you prove that it is not feasible using research, right? Right. That was your question, right?
Right. Yeah.
Yeah. Yes. So that piece is, yeah, it's good one, and I will have to think about some questions around that. It's very close to like, you know, like greedy. Sometimes, most of the time, greedy works, but just to prove whether it will work or not is the real challenge, right? It's quite similar to that. So you have to figure out like whether, in theory, of course, that if the value is possible for X, if you can always prove it is possible for X plus 1, then we have something going on, right? We can do it. Or the other way, like, you know, in the decreasing case, right? So if you can do that, then it's feasible. But I don't have a problem like, you know, in front of me where I can go and directly prove you why it will not work. But if I come across that, maybe in next session, maybe I will talk about it after the session, maybe.
Okay.
Yeah, sounds good.
Yeah.
Okay. So at this point, I think we have covered a lot of things, and you guys have access to this. And yeah, I think that's it for today. I think I will stop the share. We are almost on time, so not bad. Yeah. All right, guys. So let me stop the recording, and then we can talk about the next session ideas a little bit.